Morning. Today we'll have a guest lecture. Stephanie will talk about derivatives and gradient descent. And as I promised, we're moving a little bit from linear algebra, away from linear algebra to calculus. But this will not be real calculus. It will be just calculus tools applied to numerical analysis. Because for all of the optimization problems, you need to know what derivatives are and how to work with derivatives and how to implement them numerically. And you have so many methods to implement both integration and derivatives in numerical way. So this is just introductory lecture on how you implement numerical derivatives, where it comes from, where these approximations are coming from, and so on. So, Stephanie.
Okay. Hello, everyone. My name is Stephanie. I am actually not a professor. I am a PhD student, just like you, most likely. But I am part of the Department of Biomedical Engineering. I actually am also part of the Center for Lung Analytics and Imaging Research. Basically, anything that has to do with the lung for imaging markers, that has to be not only in the changes between inspiration, so when you breathe in, and then when you breathe out, those dynamics between two different time points. And so, yeah, I'm a third-year PhD student. Dr. Ari is actually one of my co-mentors. And I'm pleasure to be here. So a little bit of the outline for this class, and that really depends on how well and how fast we go into this class, but we'll go into numerical differentiation. So that means more of the derivatives, Taylor series, what's forward difference, backward difference in terms of approximating a derivative, and then the relationship with gradient and gradient descent. And if we have some time, we will go into some of the integration. So trapezoid rule, Simpson's rule. You know, if you remember that curve and you have a bunch of squares and you're trying to fit all these squares within the area of that curve, you know, that's what you're actually doing for integration. And integration is not necessarily something that you only do for these numerical analysis, but you do also for optimization methods for your algorithms. So yeah, this is actually very inclined with what we're doing today. Just so I know who is in which department.
Electrical and computer engineering.
Okay.
Electrical and computer engineering.
Okay.
Design.
Okay.
Civil engineering.
Civil engineering. Okay, cool. Okay, so you probably know this, but it's just a refresher. So differentiation and integration are basically operations that we use for scientific computation. This doesn't have to be necessarily only for imaging, unless in our group we're looking at changes between different images. It could also be an economic application. They use it a lot for models out there. And so if you were given a certain function, certain very noisy data, you would also be using some of these techniques or approximations for optimization, you know, vectorization of your algorithm, as well for nonlinear equation solving. So this could be gradients if you're really looking at changes between different pixel intensities and looking at the gradient changes there. We can look at Hessian matrix. Actually, one application here, if you're thinking about biomedical engineering, is we derive a lot of the blood vessel segmentation approximation through the Hessian metrics. And they've done that for a long time. Obviously, with new segmentation algorithms, we have better ways of getting those tubular structures, but that's just one method. And then for the Jacobian, again, I'm a lung person. So essentially, when we use that inspiration and expiration, you know, the changes between 2 points of two different volumes, if you were to breathe in, and you have a big, large volume, and you were breathing out, those composite changes between, at the voxel level, between inspiration and expiration, you can actually detect the dynamics with the Jacobian. And so that's another way of using it. And then, of course, you have our gracious ODEs, PDEs, anything that you could do for a little bit of what they've done, state space models, beyond Mamba. That's another way. So why do we need numerical differentiation? So this is just a schematic. You're trying to see if you can encompass with a lot of these squares within that curve and then approximate the slope, right? That's where you have numerical differentiation, right? But with any approximation, it involves errors. And so from the standpoint of computational accuracy and time, we use computers to approximate a lot of these derivatives. And even though you would want to do it by hand, that's not necessarily the case when you're using a computer. And so when you have just a general definition of the derivative in a 1D function, this could be a line, you would have the function and you would take the limit of h to 0. And that could be a very small change if I was on a hill. For instance, I was on a hill and I was to take a little bit of step and I want to see how far or how steep it is in terms of the hill. That would be your slope and that would be necessarily your derivative. And so how do we approximate if I was to take this small step, either forward or backwards? That's what we use for this approximation. And one way to do it to actually do it well is using Taylor series, which I'm not sure, are you familiar with Taylor series? Yes. And so one of the things here is that you have different ways of doing these approximations, right? We're doing, you're taking the derivative of a function, and then we're with a very small change in that infinitesimal space. How small can it be and to approximate this derivative? And so one of them is the idea of forward difference. So if I was to take a step forward, right, I want to see what's the rate of change between there. If I was to take a step backward, you would have the backward difference. And so the way that you would do it is that you would take the first function and then you would take the derivative of that and you expand this Taylor series so that you can approximate that curve as soon as possible, as much as possible to that original function. So if you were thinking about a sine wave and you were trying to approximate that sine with some of this forward difference or backward difference, then you would just take the first two, the first derivative, and then you would have this kind of error because you're just approximating that derivative. And so if you were to manipulate this, you see the function itself, you would expand the Taylor series, you would take 1/2 h to the second derivative, and then coinciding that with every single factorial, just to make sure that you have a close approximation of your actual function, right? And so this is what you have. And can you see okay, yes, you can. So this actually is what I meant with the approximation error, right? If you were only taking a few steps and taking the factorials, you have this extra Taylor series or expansion that's not being done. And that's the error. That's why it's an approximation, and that's what you're doing on your computer. So if I were to take a step forward or a step back, which one is better, right? To figure out the rate of change. Any ideas?
Depends.
Which one is going to be more accurate in terms of that differentiation? If I look over and I look down and I want to see how steep it is, and I go back and I see how steep it is, which one is going to be the best way?
Depends on the hill, doesn't it?
But they're equidistant, right? In terms of my change of position, right?
So then it'll be the same.
Now, how could you do it better how would you be able to approximate better that differentiation, that derivative?
Derivative to multiple points.
Yeah. right? You could do derivatives through multiple points, so I would probably take C, the first step forward and the first step back, and then what you could do with that. Yeah, so that's what the finite central difference is, right? You're basically taking an average of that rate of change forward, that average and the rate of change backwards, and actually makes it a little bit more accurate in terms of approximating that derivative. And again, just so you know, many times they have for the OH squared, that means basically that the function is more accurate in getting to that differentiation. As you take, obviously, if I was to take a big step forward, a big step back, the approximation will be good. But if I was to take little steps forward, a little bit steps back, you know, h as small as it is, you're able to approximate better. And so with h of 2, this just means, okay, that's going to be your function or your approximation will be better as opposed to an h of 1. And so what does this look like? Like I said, if I was to take a point forward or point backwards, this is a change, you know, how you're able to approximate the slope just using that forward difference or that rate of change with the backward difference. And of course, if you have 2 points, you just take the average, and that's how you approximate the slope. So you don't necessarily have to expand a lot in terms of the actual function when you're doing the Taylor series expansion. What's the problem with this way of doing things, though? Computationally.
A lot,
A lot, what?
iterations. You gotta do it
Iterations.
for
When
every,
you have expansive amounts of data, what do you do when you have all those operations? So you'll have more accuracy, but
take more time.
it will take more time. So what's another way that you could get closer to that accuracy as opposed to that time?
Again?
How would you be able to get closer to that accuracy without having this amount of time wasted for getting the approximation using central difference?
Finding a point in between and doing it over there.
You can. What else?
Right.
Approximate.
I'm sorry?
You approximate to the.
Yeah, I mean, you
concrete
can.
ones.
You can, but think about it more about on the terms of your Taylor series itself. What can you do?
You don't compute that much order. You reduce the order. Right.
Reduce or you expand the order? Because so far I'm just taking the first 2 portions of the approximation for the Taylor series. I'm not expanding all the way because that would make it more accurate. But what can I do with that function if I don't want to do the central difference approximation? You guys are engineers. What would you do?
Maybe you can place a point further away.
You can, again, even though you can get h to be smaller, yeah, you'll be closer. So you take steps more further away, more points. That's another way of doing things. What else?
Answer things out.
And what else? But think about you guys are engineers. You have so much. This is not just a function. This is really messy data. You don't have crazy amounts of computation resources to do this. What would you do just looking at the Taylor series expansion?
Really like try to modify the function itself, like automation to make it a more for function, and then you do the approximation.
Find the roots. Any roots?
It's actually staring at your face. Because it's the first line, if you really think about it. First 2-3 lines. So you have 2 points, you can increase the number of points to get this approximation. Just looking at the first 2 parts of the Taylor series expansion for that approximation, right? What if you continued expanding it?
It would become kind of repetitive.
A little bit. That's another way of being accurate, and being approximating that derivative without doing that central difference all the time. So yeah, I was making it harder than it looks, but so have you ever done Taylor series on a MATLAB script or Python? No? So if you were to have usually you take a curve and you take a line and you approximate it, right? You're able to get that derivative because that's your rate of change, that's your slope. But with Taylor series expansion, what you're doing every single time that you expand those operations, you get closer and closer and closer to that curve. So yes, you can do central difference and then you can expand more the Taylor series to be closer, but another way of doing it is reducing the h, so the position change. But why is that not necessarily good? The closer that you have h to be closer to 0, yeah, you'll be closer to in terms of accuracy, but computationally, why is that a problem? Think about your bits, your numbers.
They're all going to be very close.
You have all very close, but operations wise, if you were to put a certain amount,
The order increases with any term you add.
so the closer that I have, they see this as a truncation error as well as the roundup error, is that you can't necessarily have infinite numbers of decimals to be captured memory-wise from your computer. And so it will always be an approximation. You will never get to that true accurate differentiation irrespective of anything. Yeah, technically you would get close, but you have computation limitations because not everything is going to be represented in the same way that you could have it infinitesimal if I was to do it on a piece of paper. Take me at some time, but that's one way of thinking. Because you have a data, you have to do this with differentiation, but you have limitations in your own computational resources.
What you're saying is taking too many points all within like small steps of each other is kind of redundant because you're going to get similar answers or closer to each other, but they're computationally exhaustive. So
At
we
a
would,
certain point.
yeah, so we would rather take distance changes that are further apart,
Further apart, yes.
but still frequent. So
Still
we would get a better,
You don't need to do this like forward difference and like taking the average. With just one way of doing things, you can get the approximation if your h or your little perturbation is really small. So that's where this whole reason why this is here, because you are using computers for a lot of your data. If you're approximating this differentiation, eventually it's not going to be as accurate as you would think it would be. It would be close, but not there completely. Does that make sense? Yes. Yeah, Gary, any comments?
Yeah, so many times in MATLAB that you're computing things which is one number which you computed somehow equals to some constants that you wanted it to be equal to, and this is a condition for your stopping criteria or something like that. Many times the same criteria fails, while in other cases same criteria works fine. So why is that? because you're computing, let's say, square root of 2. So square root of 2 clearly has like infinite number of digits after the decimal point, right? And all of them are not predictable and all of them are different. But in computer, you do not have that full set of infinite number of digits. You have truncated number of digits, which means if you compare it to another representation of the same number, just with less precision, maybe last digit is a little bit different, MATLAB will tell you, no, these are two different numbers. So because of your last digit, which might be like 10 to the negative 14 type of digit, which is practically zero. It's not real difference. It's just numerical approximation in the last digit that you hold in your computer. MATLAB will tell you these are two different numbers. So this doesn't work. So it's always when you're using comparison of two numbers, you're saying this number minus this number, absolute value, less than some particular threshold of tolerance. This is how you do conditions in programming typically. You're not saying one number equals another number, and this is a condition for stopping something, some loop or whatever, okay? This is the same reason here. When you're doing derivatives, number one, they are very sensitive to noise. So if you have data points, they are very noisy typically, and derivatives are sensitive to noise. They amplify noise. You can think about that as high-pass filter, if you're familiar with filtering. This is what derivatives are doing. These are high-pass filters. And second, you have also truncation error and round-off error, which is done automatically by computers because you have finite length of representation of number in any computer, all right? So you cannot get it exactly. So if you will subtract this number, they will give you zeros or some random, really tiny number, but not the real number, not the numbers that you want. So it will not improve your approximation of your derivative if you go further and further with your tolerance. So stop at like 0.001. This is good enough for any kind of approximations that you do with derivatives because they're noisy anyways.
So, yeah, so it's about the accuracy then. It's about how accurate we can be in terms of, that's why you're saying bits, think about the bits. So we can't go past a certain amount of decimal points, let's say.
Because actually you won't be, like, what's the point? Also, right? But if you're really thinking about being accurate, never could be there. Never be there. So,
I have a question.
yes.
If you want to simplify the computation, is it a good idea to like reconstruct the signal, like using the sample theory?
Analytical signal?
Yeah, something like.
Yes, you can do least squares on the signal to fit the points to a particular model, and then do derivative of the analytical function, which is precise and exact, right? So this would be pretty good solution, but computationally more expensive.
But because you have to.
Or you need to do least squares first.
So there is this, we did that in terms of the approximation. And so if you were to have an h of 1, this is f of x plus h, and you're expanding the Taylor series, this is a discrete form. So you're approximating something infinitely within a very specific or finite space. And so here is just, you're seeing that as it goes with k plus 1 or k minus 1. And that's what I mean in terms of that forward difference or backward difference. You have your computers? Yes? No?
Yeah.
This is very quick to do. So you can do whenever at home. Right?
We can save time.
Yeah, we can save time.
I
But
will share the lecture. So we'll
yeah.
share the
If you've never done Taylor expansion, first order, third order, fifth order, you just get closer to that curve, right? And so this is a way to see and how well you're doing in terms of the computation for that approximation. And this is, you use a sine wave and everything. So, okay. We already did that. And let's see. And like I said, the central difference, if you're just looking at that first derivative, is more accurate. What happens? Yeah, we spoke about this. This is the round off error, the truncation error. So the finite amount of memory used for storing these numbers means that there is a maximum and minimum possible number being able to be represented in your computer. So yes, we spoke about this and here. Okay, so what happens if you were to increase in that order of differentiation? So we just spoke about the first derivative. What happens with the second derivative?
What happens to second?
If I was to, I'm making my differentiation more complex, right? So with a certain amount of function, you're doing the second derivative. What happens in terms of that difference of approximating that differentiation? What would you do?
For the approximation?
And what can you do? You have the Taylor series. Go think back into the Taylor series. You have the function, you have the second derivative, then you expand until you get the third, fourth derivative, and you expand forward to be closer to that curve. Now, if I was to take that higher order of that derivative, or like in more second derivative, third derivative, what would you do? If you didn't have your computer in front of you.
That.
Think about it. Staring at you right in front of your face, like I can see it. It's right there.
Like you change the sign.
Just sign, or what can you do?
Forward, backwards, average. I was using the first.
I'm able to approximate the first derivative using the Taylor series, right? So if I was to approximate the derivative of a sine function, yeah, cosine function, right? But if you were to expand that Taylor series, look at the equation itself, can you not approximate with just the first derivative?
Repeat.
Yeah. Some terms will repeat. What can you do? Can you do something with this Taylor series expansion?
So look at the two last equations. So to find, like, look carefully at the two last equations, first three terms after the equal sign,
Mm-hmm.
all right? So when you
Yeah.
Opposite in size,
subtract one from another, like you take the
Cancel.
first one minus the second one,
cancel out.
okay? F derivative will be twice F derivative, right? So you'll double the F derivative and second derivative will cancel out, right? If you subtract from the first one, you subtract in the second one. Look what happens if you add them together.
First derivative will cancel out.
First
Second
derivative will cancel
will-
out and you will be left with
The second
F
derivative.
points, something related to points, and second derivative. So can you compute second derivative out that sum of equations given the points?
Oh, yeah.
Just algebra.
Yeah. You don't have to look too far to doing that higher order difference. So with a higher order derivative, that doesn't mean that your computation, yes, it will get more complex, but with just the Taylor series itself, you can approximate that just using algebra. So
You'd be using the finite central difference. That's the only way you can add or
You-
subtract.
you can do that. But with a second order derivative, what happens in terms of the computation? If you were to use the central difference,
Sounds more complex.
it becomes more complex, but why? As in terms of, in comparison to just using the first derivative.
Pretty much more complex.
Yeah, I mean, it's not necessarily, but
It's like one more operation. It's
But-
not really that complex. So what
You-
happens is you need to compute, like think about that the following way. You can do first derivative as just difference between next point, previous point, or this point minus that previous point, okay? So you can do that for each pair of points. You can find that first derivative. So what is second derivative? It's doing derivative on derivative, right? So it's like difference of differences, practically. So you're taking two differences, which is your first derivative at 2 points around that middle point. And you can do that now new point, which is derivative between these 2 points, and minus derivative in these 2 points, which gives you second derivative of these 3 points now, okay? Which would be exactly in the center.
Yeah.
Right? So this is how it works. This is exactly the formula that you see on the screen. It just takes difference of differences. And you can do that as many times as you want. So you can give more differences and difference of differences, and then difference of differences of differences is a third derivative, and so on. Okay, so you can repeat that process for any order of derivative. And this would be kind of the simplest approximation of nth order derivative. And you can use more points, and then you get better approximations.
But with more level of approximations, higher order, in terms of those derivatives, what happens to the error? Does it decrease?
Increase.
The higher the order, you said the more accuracy you have, right?
You can have more accuracy, but those minute errors compound themselves.
So the errors for each one would be very small, but adding them all together would create a bigger error.
So that's in two, I mean, you have really thinking about how well I'm able to compute something that I can approximate the derivative or the difference in here, and making sure that it's accurate enough. So there's two things, right? There's errors here, and then there's also accuracy.
It's pretty safe to say that if you're using any derivatives higher than order 2, it's most likely just pure noise computationally. Like if you have real data that you measured somewhere something, voltages or whatever it is, and then you need third derivative of that, it will be practically noise. Nothing to do with the actual signal. Unless you're using like very computationally expensive fitting of the function and all of that stuff.
A lot of the ventilation data, you could do that too. Yeah, so this is two things, right? You have the forward difference, backward difference, central difference. You have changes between accuracy within this approximation. And then you have with every higher order in terms of that differentiation, you have this tug of war between accuracy, but also that approximation error. So are we good for now? Yes. And so this, you can do this on your own time, but you can do this in MATLAB given the exact derivative being the cosine, and then seeing the forward difference approximation, the backward difference approximation, and also central difference approximation. And you'll see each one of the curves, and it's actually pretty well defined in terms of as a proof of concept. So when you have time today, anytime, you'll see this in terms of what's happening computationally in the backend.
Then a little bit of noise and see how horrible this works.
Yeah. Yes.
I wonder, is that possible that error becomes infinity? More and more orders.
Nothing in computers is infinity.
I mean, maybe like the error is bigger than just you can expect it.
Error in derivative cannot be bigger than the maximal distance between consecutive points. So unless one of your points is at infinity, error cannot get bigger than that. Like, unless the points are kind of one on top of another, right? So this is derivative which is infinite. And then in computer, you obviously get something finite, infinite, so error will be infinite, but this is the only case. Typically, you don't have that kind of case.
So this is again, this is finite approximation for a reason because of the whole limitations within your computer resources. Okay, so if you're using your computer to approximate, you will never have this accuracy. So,
And if you increase the number of terms or a difference,
Mhm.
increase the number of terms in the backwards, find the average, the error will still not kind of improve.
the error will decrease. Yes,
Error decrease.
it will decrease.
Uh,
But depending on the function or the type of data that you're working with, like we said, it could take some more time, more resources. So a way to approximate this, and this is you're using a stencil. You have a set of points within a line, and then with every, if you were to come to have, you were to have a line, and you're trying to see how well it is in terms of the distance from that single point, from the forward difference and the backward difference. You can actually compute that, expecting this h or discrete way. So if you were to have, f of x plus h, and you were to put a number to it, then you have this finite difference, right? And so the more, like we said before, the more points that you have in your stencil and your line, the higher accuracy that you would have, and then therefore a smaller error within your approximation. So that's just another way of constructing whether or not you can approximate as well as you can for your certain function. Yeah. Good. Okay. Who has taken image processing? Yes. So many of these approximations are numerical differentiation. If you're thinking about an image, you can do that in that rate of change between maybe even for if you're thinking about CT image, intensity values differences. But in this case, you can also use it as a filter. And a lot of times what you do is that you can see that rate of change for edges, how well I can detect those edges within that person or the changes across from one pixel to another. And so if I was to, this is just another way of approximating or using the numerical differentiation in a 2D space, for instance. So in MATLAB, you can take different filters. So Sobel, another one, if you're using Canny is another one that you can use for your filtering. And these are all ways that you can do for edge detection. Yes.
Have about 5 minutes.
Okay, good. Okay, so this was like a tiger, and you're trying to see the edges within that tiger, and you're able to get that filter through numerical differentiation. Now, does anybody know what this is? You know. What is it?
Gradient.
Okay. What is that used for?
Pretty much to find, explain it. It's just a path to find the closest to the lowest loss.
The lowest.
Like finding a certain direction of derivative.
Yeah, you can look up in terms of certain direction of derivatives. That's a gradient. You can see like a positive gradient or a negative gradient. But in the context of models, when you're trying to reach convergence, everybody knows convergence is. Yes. What is it?
which means you're smaller than certain values. Infinity.
If I was thinking about a classification problem, training a model with a classification problem, and I'm trying to see how well my model is doing, why would you use this?
To converge to one label, like when it's figuring out which label it is.
Yeah. I don't know what's what.
You know, okay, so it's okay. So, let's just say I am a bird and I'm trying to get to a certain destination. And eventually I'm getting lost and getting lost and getting lost and getting closer to the destination, but not necessarily to the steepest way that I need to be. The way that you're figuring out how well I'm getting there is through gradient descent. How close am I to being at the point where I need to be for my model to be accurate? I'm classifying well. If I had, for instance, I was healthy and I have two classes in terms of healthy and then COPD. If I'm doing a model, I'm preparing and training a model, how well am I getting to that point of convergence with the most accuracy possible? Yes? Okay. So we use gradients, this aspect of numerical differentiation a step further when you're looking at optimizing your algorithms to getting closer to that accuracy if you were thinking about a classification problem, right? And by me being a bird, a way to get to my destination or retracing my steps, you would go into back propagation. So I'm retracing my steps to where I was actually closer to my point. So that's another thing that you would expect. So the gradient here, yes, we have all ways to get to there, different loss functions to get there. But it's actually very pertinent to this aspect of numerical differentiation.
So if I get you right, it's like finding an optimal solution, finding the optimal solution, and then this is the kind of space within kind of possible solutions, and then the optimal solution will be kind of where they converge to get the best accuracy out of the possible.
Are you familiar with partial derivatives? Yeah, so regular derivative is talking about one variable and you're taking practically slope versus the function, slope touching the point, and that slope is a derivative, tangential line, angle. This is direct relation to derivative, okay? But when you have multiple dimensions, you have derivative in each direction, right? In x direction, y direction, z direction, you have derivatives, and these are partial derivatives. In partial derivatives, you hold the function completely constant in all other dimensions, and you measure in derivative in that particular direction. All right, so you take a derivative in x direction when y, z, and other variables are constant, okay, and you're thinking about them as constant numbers, okay, like constants. And as you know, if you do derivative of something times constant can go out of a derivative, right? So you practically ignore it in the computation. So thinking like how much something is changing in particular direction. What is the rate of change in a dimension, in particular dimension, okay? So these are partial derivatives. Gradient is list of all of the partial derivatives, which is d to the x, d to the y, d to the z. So it's vector, which includes all of the partial derivatives. This is what gradient is. What it tells you in practice is the direction of maximal ascent. So if you draw in all of these derivatives as a vector, because you will have n components in n-dimensional space, let's say two-dimensional space, okay? So you have d to the x and d to the y of particular function. So you'll have like two values. So it will be some vector with two values, two components in that vector. These values will point to the maximal ascent of the two-dimensional function, like where you should go. So if you're looking for minima of that entire two-dimensional surface of some kind, and you're looking locally, so you can check only locally. You start at some initial point and you check locally, where should you go? You should go to the maximal descent, right? This is logical thing to do. But gradient showing you maximal ascent, which is opposite from the direction. So you go in the minus gradient direction, which is opposite from maximal up direction. Okay, and this is the overall idea behind all of these gradient algorithms, where you want to optimize, so it's optimization algorithm, which is minimizing something, just go in the most steep direction, which is shown by a negative gradient.
Everybody got that? What did Dr. Ari say? Just to double check.
So
There's a lot of things.
And another way of saying things, what he just said in terms of gradient, what you're using gradient for and how you're actually doing it.
He said you use it to calculate partial derivatives, find maximum ascent. That's the general idea.
He said much more than that though.
yeah, with so if you find the derivatives of all the functions involved independently, you can get kind of a space that represents the derivatives of all the functions. And then if you get the gradient will give you the maximum ascent, but because you want the optimal solution, you have to go to the opposite of the gradient direction, and then that will give you the optimal solution.
So it's a multi-directional differentiation, right? So yes. So just a little bit of the intuition here is a gradient tells us the direction of where things are going. And if you're thinking about negative gradient, that's giving us the direction of the greatest decrease. But if you're in a certain space, X, Y, Z direction, you're actually getting all those changes all throughout, as what Dr. Ari had mentioned. So here it's the same thing, right? You're with small enough steps, either in the direction of the negative gradient, the function will actually decrease in value. And this is idea of how small is small enough is still applicable here. You know, just because we're just looking at a single function, let's say a sine or a cosine wave, then aspect of that multidirectionality for approximating that derivative is still applicable, but in a greater sense. And that's what's happening in terms of gradients. And so this is a function, and you have the derivatives if here is negative x. And so you have different gradients at every single point in terms of the direction. So this looks very simple. If you're just trying to describe this image, where direction is it going?
Left to right?
Pay attention that signs on the left are positive and signs on the right are all negative. Yes, your gradient, which is in that case just derivative, have only one component to the gradient, right? It's positive on the left, which means it's pushing that direction to the positive x, and on the right it's pushing to the left,
Yeah.
negative x. So it's pushing to the peak, to the direction of the peak on both sides. Pushing stronger when you're farther from the peak also. Closer to the peak you become, it becomes closer to zero, which is pushing less.
So in terms of direction, you mean it's converging at zero?
So this idea, like Dr. Ari said, you know, how far you are, that pushes more into the center with more order, I mean, not orders of magnitudes, but with more intentionality in this case, and closer to zero, it would be less, but you still get to that point of convergence of zero. So the gradients on this side of the peak are positive, and then the gradients on the other side of the peak are negative. So the gradients are all about directionality. Yeah, so sign of the gradient point shows you that the direction is actually going uphill. Coming here, and the direction is actually this way. So what happens with 2D gradients? You're to have an image with different you have whole vector. It's not necessarily one-dimensional anymore. What happens to those partial derivatives on the x and y axis? Just looking at the image itself. Where is the direction of that gradient?
Going to zero.
Go into the
Going to
center,
zero.
in the center.
It's the same picture, it's just now.
Yes. So the same thing here. And so that same directionality is no longer like we saw into a line, but within a 2D space, it's still converging on that single point. The direction is still uphill. And so as you can see from the direction of the arrows, every single arrow is a gradient, right? All within the aspect of directionality. And as you can see, you know, if you were to have many intensity values, or they're still convergent at that zero peak in the center, as you saw here. And this, like Dr. Ari said, is multi-directional. You're thinking about it more on terms of an XY space. So if you have a vector within, that's the red line, going uphill, it's actually the area or the direction of the biggest step towards convergence. And then you have the ones at negative g, so that would be the other side, and that's the point of the greatest descent. So you're actually getting those two portions of the gradient in terms of directionality there. And then of course you have the green arrow, which is how it is perpendicular in terms of that area for the steepest or the uphill direction. So, and this is just another way of seeing it. So if you were to have all these points and within a whole circle of x, y, z, x, y, x, y, x, y, that's what you would have in the end here. Does that make sense? Yeah. So in terms of the gradient descent algorithm, we spoke about that we usually iterate things until we reach convergence. That point of maximum accuracy, you do this for segmentation, you want to get highest dice score, you want to make sure for classification, you want to be closer to a good AUC, X, Y, Z reason. But every aspect of that iteration is dependent on that stepwise changes, and that's the learning rate. Why is gradient descent or this gradient descent algorithm applicable from this numerical differentiation or approximation? What are you doing after every epoch that you're training something? You're minimizing the loss, right? So this idea that this gradient descent algorithm, the direction of gradient descent, you're getting closer and closer and closer to that point of convergence again, depending on what you're doing. And so, yes, we started with a forward difference, backward difference, central difference here. But if you're thinking about it as a function, optimization function here, you really have to think about what are the best steps to get to the point that you need to get to your overall point that you're trying to get for that convergence. And differentiation is one way.
Why? So I don't have an engineering background, so some of my questions may be.
No, it's okay. Go ahead.
So why don't you just use least squares I mean, we did least squares as an optimization algorithm. So why don't you use that in this and to solve some of these problems?
Let's think about more of your application. What do you usually do? What do you usually work on in terms of data?
I am in a neurophysiology lab, and then when we get our what we call the peristimulus time histogram, which is for a stimulus, the mean firing rate across time. So we sometimes fit functions and see whether the response of the neuron it is saturating or the peak or I mean for those functions. Yeah. So if I want to fit a function like a very good function in 1D, whatever function that I want to fit between that and then the predicted values, I can kind of use least square to minimize the error to get the best approximation of that function.
You can use least square in that case, right? But this is more of, if you're really thinking about,
It's a different problem.
yeah, it's a different process.
So here's the thing. Why you need in general gradient descent, kind of motivation for overall optimization using gradient descent or any other gradient-based methods, because there is an entire family of gradient descent or gradient-based methods in general in optimization. So what happens is this works when you do not have the entire function and you don't have all the data points. You don't want to compute all of the possible points for your cost function, and it will be too computationally expensive to build that entire surface. Because if you have the entire surface, like analytical function, let's say, okay, it's not a problem just to find minimum of that function, right? Just look at the minimum point, just compute minimum of all of the possible points in your function. You will find global minima. Gradient descent even not finding you global minima, it finding you local minima close enough to your initial point from where you start to descend down to the closest local minima. And you can have global minima much lower than that overall. But the thing is that you don't have that entire surface in practice. You have only local measurements around your initial point, and then you measure a little bit more, and you descend a little bit more, and then you measure a little bit locally more around that point that you are right now, and then you descend a little bit more. So you are computing your cost function, which you want to minimize as you go with a descent. And you don't need to have like to compute it at all points, okay? Because your space might be million dimensional, okay? Like go and compute function in million dimensional space. There is no way that you'll have enough memory even to store that function, okay? So you can store only local tiny neighborhood and to see where the gradient goes in that neighborhood until you converge to minima, which is local minima typically. But if you have all of the points, just use least squares or just minimum of the function or any other way, you don't need gradient descent for that case.
The reason, so Dr. Ari made a good point, is that you're still within a finite space. Okay? You don't have all the data. And so you're still approximating here, you know? And so that's why the gradient descent here is applicable. There is one way, and then I've been testing different ways for just expanding that gradient descent algorithm. And one thing that we actually did is that, have you ever thought about ants? Ants, you know, how do they work together? If you had a bunch of ants and they knew about the direction of your global minima, if you had them all together and have a certain space of communication to get to that global minima, can you expand or make that gradient descent algorithm even better? So this aspect of swarm intelligence for a gradient descent algorithm. And that's another aspect that you can do for that approximation for how well you want your, how good your model will actually be. So this doesn't just stop here. You can think about it even further out with just systems that are in our everyday life. And I brought this up, I wasn't going to bring it up, but we've been using it. And actually, we took a piece of a puzzle of a face. Let's say I had a piece of my puzzle of my face, and just using different ants or like I have like birdoids, you're able to get to that portion of the whole puzzle being done. And so if you're thinking about gradient descent algorithm for optimization, how can you hit it from every single point so that you're able to get to what you need to be in terms of that approximate global minima, while not being so computationally expensive. So you're engineers. This goes beyond this. So you have to really think about how are other ways that you can optimize things if you don't have the infinite computer resources that maybe some of the industry competitors you would have. Yes.
The entire goal basically is to be as accurate as possible with the least amount of cost.
That's the whole point. And you're in academia right now, so you have to. You have to. There's no way that you get, and I mean, maybe if you go into industry, you have infinite amount of computational resources, that's a different story. But when you're trying to do some sort of optimization algorithm, making things better for yourself, you don't have that luxury. And so you all have your own thesis, your own models that you're working on. How do you make this as resource constrictive, as in limited, in a way that you're still getting to the point that where you need to be? So, okay, so you have a curve, a function of x squared, and if you're trying to do these stepwise of 0.8, you're able to get closer to that direction, right? So the x is 0, stepwise of 0.8 and -4, and then you can continue forth until you have that same direction or that same point of convergence. So you get closer and closer to 0. And so if you think about it, infinite space or maybe infinite amount of points, and yes, this case is not many, it's like 9 steps. You get closer and closer and closer to that point of the direction going downhill. So the whole point, again, how do you get there faster without just doing step size changes? Any ideas?
Can do the computation around your around your center, because you see that actually there's a straight line that can represent their average.
But you have no idea, right? How can you approximate? You can probably do that one line, but you have no idea where it's actually going.
So an idea from how we do experiments to kind of determine the threshold of vision. So one method we use, I don't know whether it works here, is from the initial, you take a giant leap, kind of a random giant leap, and then based on the response, I mean, over there, because you are looking for kind of the minimal response, from there, when you compare that to the minimal response and it's not that, you take a second giant leap in maybe, so if your first giant leap is above the minimal response, it means that your next response should be a leap in the opposite direction.
Yeah.
But if the leap in the opposite direction is also, it's kind of greater or it's less than the minimal response you want, it means that you also have to take a giant leap in the next direction. So that random will help you kind of get closer to the point you want in time, as compared to doing it stepwise one after the other.
And that's what you're doing here. So what are other things or other parameters that you can be flexible to get to the same point?
There's a Taylor series.
No. I mentioned it very briefly earlier.
Just like an adaptive step size.
An
maybe?
adaptive step. What's that adaptive step in your algorithm, maybe? When you're trying to get closer and closer to that accurate. So what can you change in your algorithm when you're training something? You're training your model to get, let's say, Dr. Harry's student trying to get those very small pulmonary vessels, and you're trying to segment them out as much as you can, depending on the type of loss function. How do you get to that point quicker in a way that's faster? Through one of these, thinking about gradient descent as an optimization algorithm. Your learning rate, right? We mentioned that. What's something else?
You say?
Learning rate.
Oh.
What is learning rate?
So learning rate is basically kind of like that portion of getting to how fast you're doing things in terms of the computation for that gradient descent. So if you take some space or wiggle room to get to the next point or closer to that point, then that learning rate is going to change as well. So that's one portion to change within your algorithm so that you're closer to that global minimum. So what's something else you could do? Learning rate, what else we spoke about? I know there's many electrical and computer engineering. I know that you're doing this every single day. So what are you doing in your algorithm so you can get closer and closer to where you need to be? I'm looking at you. I know that you know. I know that you know.
I'm not sure.
I mean, yeah, those function. What
Initial
else?
condition, the initial phase value. So for this one, instead of starting at 16, maybe if you start at 4 or 2.
But I'm thinking about more, what can you do, for instance, to make your training faster?
Take less point. Any less.
Okay, increase learning rate. I know there's more.
Training size.
Okay. Let's say that I'm giving you a bunch of images where you need to predict the outline of a dinosaur. How would you make sure that the predicted mass for that dinosaur is where it actually needs to be? What would you do to your algorithm to make sure that you're being accurate while still getting to that predicted mass? We said learning rate, we said something else.
The epoch.
Epoch, yeah, increase the epoch. What else? But Sarah, do you know what I'm trying to get at?
No.
Okay.
You have too many things.
I have too many things. I have too many things.
The adaptive gradient descent.
Adaptive gradient descent. You can do that actually.
Moments.
Yeah, you have so many. Actually, you have many parameters that you can fix within your algorithm to make it not just faster in terms of that convergence, but more accurate. Now, depending on the data that you're working on, I'm going to invite you to look at different Kaggle computations. There's actually one just now. You're all mostly signal people, right? EEG data. How can you optimize that prediction for someone who's going to have a seizure? A lot of people do that here by optimizing that gradient descent for that prediction. Right? So think about it. Fiddle around with your algorithm and how can you get to that approximation for that predicted value, predicted mask or whatever, just by tweaking certain parameters. And so I got a little bit sidetracked here, but the way the step size that you're doing for that approximation actually does matter. Right? Whether or not that step is big or small, it's going to affect the way that you're getting to that point of convergence or that point of maximum, I guess, the direction, true direction. So just like before, yes, you can have different step size to be the same all throughout. But if you go and keep on going to the step size, continuing forward, you'll get to that overall direction. And if you think about it, and so we spoke about global minimum and local maximum just for visually, this would be your local minimum. You're trying to be here. And so when you're thinking about it, you're seeing obviously getting all these numbers within your algorithm or your output, you know where this is actually going to be just based on this or approximately, right? So how big or how small those step sizes are important to get to that point of convergence or true convergence.
Very critical question here because this is the biggest disadvantage of gradient descent methods in general, that you're not getting global minima, you're getting local minima, and it will be global only if this is convex optimization, which is relatively rare case. And these optimization problems are very nice when you have convex type of shape with only one global minima. But in most cases, you have tons of different local minima and you don't know where you will be stuck with that particular minima because you don't have the entire surface. If you would have entire surface, you don't need gradient descent, you just find global minima. But you don't have it, so you need to look on particular trajectory. And this is why people start with multiple different initial points, trying to converge better somehow, but it becomes more computationally expensive. And also choosing step size, which would kind of converge to a particular point. But if your step size is very small, it will converge really slowly. If your step size is too big, as you've seen in the previous picture, it will jump to another local minimum, which is not where you want to be. Okay, so you have tons of different issues that need to be resolved with gradient descent. And again, people have plenty of solutions for any of these problems, but it typically increases computational expensiveness of the algorithm. Okay, this becomes not that simple anymore.
Again, you know, you're engineers, there's so many options of how to get to that global minimum, but I would invite you to really think about how you can get to that point of convergence faster without adding to that computation time. And I think it's 10:45. Sorry. So just something to look at for now. We did numerical approximation using for differentiation, and then gradient descent as the next step. And so here is more about numerical integration. This is something you can look at. TorchSquad has different ways of optimizing algorithms based on this whole aspect of numerical integration, from trapezoid rule, Simpson's rule, Boole's rule, Gaussian, quadrature, Monte Carlo integration, which is, I'm sure you've probably seen before when you're trying to get, they use that a lot for registration problems, for registration of images. And then Vegas Enhanced. So I would invite you to look at Torchquad, how you can play with different aspects of their parameters to go forward. So that's it for me.
We'll have another lecture on that as well, another guest lecture. Okay, this will be probably a few weeks from now. We will continue talking about integration of the column methods and other things related to that. Thank you very much.
Thank you.
Thank you.